Yes. So today I'd like to uh, welcome Professor Marta D'Elia, who is the Director of AI and ModSim at Atomic Machines and an adjunct professor at Stanford University, ICME. She previously worked at Pasteur Labs, Meta, and Sandia National Labs as a principal scientist and tech lead. She holds a PhD in applied mathematics and master's and bachelor's degrees in mathematical engineering. Her work deals with design and analysis of machine learning models and optimal design and control for complex industrial applications. She's an expert in non-local modeling and simulation, optimal control, and scientific machine learning. She's an associate editor for SIAM and Nature journals, a member of SIAM Industry Committee, the vice chair of SIAM Northern California section, and a member of NVIDIA Advisory Board for Scientific Machine Learning. For today's talk, it would be mainly about particle accelerator simulations. So when we talk about in the context of scientific and industry applications, one has to deal with unstructured space-time data obtained from numerical simulations. So today, the talk will be on overcoming the computational challenges in particle accelerator simulations using graph-free point networks, as well as with graph neural networks. And in point networks, it does not require a connectivity information as opposed to its graph counterparts. So the framework that will be talked about in today's discussion will be trained on high-fidelity simulations on electron beam acceleration, capturing complex non-linear interactions among macroparticles distributed across several initial state dimensions and machine parameters. This framework accommodates key symmetries inherent in particle distributions, enhancing stability and interpretability. And this research is found to offer a powerful approach in reducing computational demands in particle accelerator simulations, contributing to advancements in real-time optimization and control. So over to you, Professor Marta, for the rest of the talk. Thank you.
Thank you very much. You gave my talk for me. What else am I supposed to say? I'm joking. So thanks a lot for having me. I'm happy to share some of the work that I've been doing with my colleagues at Stanford, and in particular, one PhD student that is finishing up her PhD this year. I still cannot share much about the work that we've been doing at Atomic Machines because it's a startup that is still in stealth mode, but hopefully very soon we'll be able to give presentations also on the work that we do here. And I'll say just a little bit at the end in this regard. But yeah, so everything that you're going to see today is supported by Stanford University and in particular by the SLAC Center. I'm going to start by presenting the surrogate models that we're interested in. So the type of surrogates that we're after, in particular in design settings, scientific and industrial design settings. I'm going to focus specifically on graph neural networks because these are the networks that I've been using since I moved to industry for several reasons, and I'll explain some of them. Before jumping into the specific application that I want to talk about today, I'm gonna give a few thoughts, let's say, on the use of graph neural networks in the context of numerical PDEs, and these are just comments that come from having used these networks during the last few years in the industrial applications. And then I will move to particle accelerators, and I will show our preliminary results. This is very much an ongoing work. We didn't start this work a long time ago, so this is, I welcome all possible feedback here. I will talk a little bit about our next steps and some other ongoing work at Stanford in the context of graph networks. As I mentioned earlier, the main contributor here is Tiffany. Tiffany is a student at the Institute for Computational and Mathematical Engineering at Stanford, and all the results that you're going to see today are part of Tiffany's thesis. The PI at SLAC is Orly, and Eric Kropp is also a scientist at SLAC. Murray is a postdoc at ICME, and Eric Darv is the director of ICME and the co-advisor for Tiffany. Okay, so what are the problems we're interested in? We're interested in industrial and scientific design scenarios. So finding the best configuration of a system, finding the best shape for a particular object. And when we are in this context, the main task is the solution of an optimization problem constrained by a multi-physics, multi-scale, multi-phase system of PDEs. And the challenge here clearly is that at each optimization step, we need to conduct a very expensive computation. So there are time and cost concerns. Another challenge that I started facing once I moved to industry and once I started dealing with all sorts of codes, it's not really the topic of this talk, but it's something that I always mention, is the fact that oftentimes the simulation is performed in a simulation tool that doesn't necessarily live in the same environment as the optimization tool. So there are all sorts of interoperability concerns that need to be taken into account. So how do we circumvent the primary challenge here? Well, clearly, as so many people in our field, we're looking for fast surrogates that fully reproduce the solver behavior in terms of accuracy, but also in terms of flexibility. And by flexibility, I mean the ability to reproduce thousands of scenarios that may come up during the optimization process as we explore the design parameter space. So in clearly machine learning terms, we want these surrogates to generalize with respect to operating conditions, boundary conditions, and initial conditions. And operating conditions include, for example, geometries. We also want differentiable surrogates, or at least we would very much like to obtain differentiable surrogates that can be used with gradient-based optimization algorithms and can be used with these algorithms in an agile manner. And so in this case, I'm going back to that interoperability concern that I mentioned before. So not surprisingly, the surrogates that we are pursuing are neural networks. So clearly here I have an oversimplified slide with an oversimplified network. The reason why I'm reporting this is just to set the ground for what I'm gonna talk about after and describe basically the type of networks and the type of training that we consider. We consider, in a way, fully data-driven approaches where we're given a data of input-output pairs for a system. And our goal is to find a network that fully reproduces the solver behavior. Here I'm reporting the simplest equation ever, a diff-grad operator, where the solution is P, and we have some parameters, the diffusivity, the forcing term, and the geometry. The way we approach this problem is to basically have as the input of the neural network nodes corresponding to every degree of freedom in the domain, to which we associate either the solution in a time-dependent setting or all the parameters in a stationary setting. And the output is once again of the dimension of the degrees of freedom of the simulation or the computational domain that we're considering. And we associate with every node clearly the state or the solution. As I mentioned, this is fully data-driven, meaning that the training is simply minimizing the difference between the network evaluated at the input minus the corresponding states. So this is the setting we operate in. This doesn't mean that we don't consider any physics, but what we don't do is to add physics in a soft constrained manner where we add the residual of the equation. We can chat more about why we don't pursue this. I think the main reason is that the training becomes more complex. We're faced with the problem of finding an optimal weight and all these things. But again, this doesn't mean that we don't want to embed physics. And in fact, physics-dependent interactions in the node space can be included, and that's how we proceed in the network. So if every node corresponds to a degree of freedom, and we know that there are physical relationships between nodes, we can, in a way, embed them in our network, and I'll show an example of this. And then we can consider modified architectures that naturally embed invariances, for example, or any sort of physical properties such as rotation invariance or translation invariance. The philosophy here is that we try to embed the physics as much as possible, but also in the cheapest way possible. Other networks, other features that we are after are clearly accuracy, and usually this corresponds to depth, but at the same time, we need to ensure stability as we go deeper in the network that we are developing. And I'll say a few words on this later on. We're not necessarily after interpretability, but I have to say in industrial settings, we've observed that if physical properties or physical interpretations can be inferred from the network, people that are not that familiar with machine learning are more inclined to believe in the power of machine learning. So this is one concept of interpretability, so recognizing physical features, for example, in our machine learning results. Another interpretability, which I very much like, is recognizing in the network some physical or mathematical models that, as numerical analysts, we know how to deal with. And so I think the best example is neural ODEs, where the network is clearly an ODE, and we have all the tools and years of numerical analysis to analyze it. Being resolution independent, as much as it's a feature that can be very useful, for example, in multi-resolution settings, so multi-fidelity settings, it's something that in industrial context we really never pursued. Maybe for the lack of multi-resolution data sets, but maybe more because there wasn't an interest and a push for it. So we needed to be we always needed to be very practical. But during, for example, my Sandia times, that was something that we tried to pursue and obtain in our networks. And in the networks that I present today, switching to an architecture that becomes resolution independent is in a way straightforward, but it does make the network more expensive. Okay, so the choice of graph neural networks comes from the fact that they're very flexible in a way, and they allow us to deal with unstructured data in a very straightforward manner. The base architecture that I've been using for a while now is a message passing neural network, graph neural network. And we've been considering variations based on this vanilla version. The closest to this, and probably the architecture that made this type of networks explode, is the mesh graph net architecture. And this is a simple cartoon that illustrates how it works. And by starting from mesh data or point clouds, we go to a graph representation. This is very easy when it comes to some specific discretization. If you think P1 finite elements, there is a one-to-one connection between the mesh and the graph. When it comes to data, when it comes to point clouds, we have to build the graph, but there are many ways to build graphs out of point clouds. And then we process the data, we obtain a graph prediction, and then we can go back to the original data format. At the processing stage, so where we actually do inference, there are three fundamental steps: encoding, processing, and decoding. The encoder is applied to every element of the graph, node, and edge. And it projects every component of the graph in latent space. So this is edge-wise and node-wise, and that's why we can generalize to different dimensions, for example, different geometries in the context of meshes. There is a processing step, which in the context of message passing is aggregation of messages coming from neighbors. And then we decode, and go back in physical space. So this is a very general architecture, and it's very effective in some specific context, and it's less effective in different physical contexts. And that's what I wanted to talk about in the next couple of slides. So although very effective, for example, in time-dependent CFD settings, when we apply this architecture just out of the box to mechanics problems, there could be challenges. So if we think of stationary mechanics, we have that intrinsically in the problem. We have a fast propagation of information across the whole computational domain, because, for example, stress in any at a point depends on all the other points. And when it comes to message passing graph neural networks, the messages are passed in a very local way. And to pass information from a point in the domain to, let's say, in the opposite side of the domain, we need a lot of messages passed. And this can be done just by adding layers to GraphNet. But what can happen is that we lose stability. And so this is the contrast between depth and stability that we need to take into account. And GraphNets can present vanishing or exploding gradients as we go deeper and deeper. And so we need to find a way in the context of mechanics to accelerate message propagation, not in a way that compromises stability of the network. Another issue with the basic architecture is the fact that rotated or translated geometries are considered as completely new geometries, while we know that in the context of mechanics, even if we rotate or translate a body, the results should be identical. So in the past, for taking care of the first problem, so the fast message propagation, we introduced a couple of approaches. Some of them actually turned out not to be the most efficient in very large scale settings, and I'm going to talk about it. So one approach that is actually very, very efficient in terms of accuracy is to add virtual edges within the graph. So edges that don't come from, for example, sites of a triangulation, but they are just virtual edges. Clearly, the drawback here is that we're adding degrees of freedom, and so we're increasing the computational cost. Another approach that at the beginning we thought was very smart is to proceed in a multi-grid type of way, where we start from a graph and then we do pooling and we go to a coarser graph, and we keep doing this operation until we reach a certain level of coarseness. And the effect of having a coarse graph is that the information propagates very fast in the domain. And then we go back to the original resolution. So what we did in this case was to do pooling with the top K type of algorithm, which is the same algorithm that is used in GraphNets. The problem, though, was that GraphNets are used in classification contexts, and the effect of a top K algorithm is that the latent graph or the coarsened graph may be even disconnected, which is really not beneficial in physical context. And so what we did at that point was to take the power of the graph to reconnect the graph. Turns out that in very large scale situations, this is prohibitive. It's not a good approach. And so what we're working on right now are smarter pooling approaches that still select relevant nodes in the coarsened graph, but then that keep the graph connected as it physically should be. So this is just a maybe too long digression in the mechanics setting. For
Just
CFD,
one question.
Yeah.
So are you also encountering oversmoothing issue when you go deeper with the depth of the network?
You mean in terms adding more message passing blocks?
Yes.
Yeah, sometimes we observe like vanishing gradients. That's what we observe.
Okay, okay. But how about oversmoothing? That's a typical issue in graph neural
No.
network.
I think for us, the vanishing gradient was the first symptom, and based on that, we just didn't go any further. It is very possible that you also observe that, but we didn't get to that point. Like
So are you
Yeah.
using batch normalization? Even with that, you are getting these kind of issues?
Are you asking if with batch
With batch
normalization
normalization, yes, yes.
and are you asking if with batch normalization we don't observe it or we observe it?
No, I mean, usually with batch normalization, these kind of issues somehow mitigates. So I'm not sure if you're using that one.
Yes, we are using batch normalization.
Okay, okay, okay.
Yes, we are. I think it's just at some point when you go very deep, and by very deep, I mean try to make a point that, for example, is here, connect to a point that is here, that really is asking too much. And it's also too much in terms of parameterization, right? Like you're really having way too many parameters at that point, and it becomes very expensive. So in general, we would like to avoid depth also because it becomes super expensive.
Okay, okay. Thank you.
Thanks for the question, of course, and feel free to interrupt me. So in the context of computational fluid dynamics, we have similar issues, but also additional issues, in my opinion. And one issue is that all the nodes are treated in exactly the same manner, although we know that there is like a preference in terms of where the information should go, because there is a flow, and we know that some points affect other points in a different way. The other problem that is very similar to the problem that I talked about for the mechanics case is steady CFD, where basically the only inputs that we have are the geometry and the information on the boundary. And according to our approach, where we want the input to be the whole computational domain, basically we're left with a lot of empty nodes in a way. And so probably using this type of graph nets is not the best thing to do. But going back to the preferential direction, something that we implemented is a graph attention type of network, where we basically treat differently messages coming from certain nodes. And so when we do the message aggregation, we put a weight on certain messages based on where the information is coming from. And we give more weight to messages whose direction is in the same direction of the flow. And this is just how the weight is computed by the cosine between the edge with a sign and the velocity. And this is an example of what I was mentioning at the very beginning, embedding, node information, like physical relationships between nodes within the network. Okay, so now that I've given this very general comments, we can move to the specific application that I wanted to talk about, and it's developing machine learning surrogates propagation. Once again, what we're
Marta, your voice is breaking.
interested in is design. We want very quick processing. Oh, I'm so sorry.
Can you hear me?
But I try to. I'm not much doing. I can hear you, but can you hear me fine?
Yeah, now I can hear you. Yes.
I'm going to try to stop my video, maybe
Yeah,
by
sure.
minimizing data transfer.
Sure.
It gets better. You can hear me fine?
Yes.
Okay.
Yeah.
Okay. So in this situation, we want to solve the ultimate goal is to solve design problems for beam customization, and also to achieve accelerator settings that weren't achieved before by human intuition. And also by having very fast surrogates for beam propagation, we can do real-time control. Now, I'm in no way a particle accelerator expert, and this is why we have domain experts in our team. I still want to give a very general description that is in no way rigorous, but so these are machines that use electromagnetic fields to push charged particles to very high speeds and energies. These are used in many applications. Medical applications in particular are of high interest. The key ingredients of these machines are the fact that particles are accelerated and guided by electrical and magnetic fields, and oscillating electric fields are synchronizing the particle motion, and the beam dynamics is what governs the particle trajectories using magnetic elements, dipoles and quadrupoles. So the key components here are the radio frequency cavities, which are responsible for the oscillating electric fields, and the magnets that are responsible for bending the particle beam and changing its focus in a way. So what are the challenges? So these accelerators have dozens to hundreds of design variables, and up to thousands of variables that we can monitor. Experiments are expensive, actual experiments are expensive, and clearly simulations are used in place of these experiments. But even the simulations are incredibly expensive, and being so expensive, and we're talking hours, clearly real-time control, but also large-scale design becomes very, very challenging. Why are the simulations so expensive? Well, because this is a very highly coupled and complex system with nonlinear and collective effects that involve Maxwell's equations and the equation of motion governed by the Lorentz force. Simulations are usually particle in cell, electromagnetic simulations, and as I mentioned, a simulation that reproduces an actual experiments can cost a lot and can last for up to 10 hours. And so clearly, given the parameter setting, given the richness of the parameter space and the very high cost, simulation cost, this is a huge opportunity for machine learning to be impactful. There has been prior work in this direction, and orally, the PI SLAC has conducted some work, obtaining very impressive speedups. What we're trying to do now is to get more accurate and more interpretable results by using exactly graph nets, but also we've been exploring point nets. So we want to improve on what was done before and provide not only a map from the initial configuration to the final beam configuration, but also a time advancing type of architecture. So what are we pursuing? We're pursuing a surrogate model, the machine learning surrogate model that approximates the accelerator behavior over different settings. And the ultimate goal is to find optimal setting. What we've done so far is to find an input to output map where the input is the initial configuration of the particles and the output is the final configuration of the particles. We're working right now on an autoregressive architecture that also has time evolution. We prescribe permutation symmetry and rotation and translation invariance to the architectures, which is needed by the physics. So what are the data? We have thousands of point clouds. Every point cloud has 2,000 particles. And the attributes for every node, let's say, either a point or a node in a graph net, are the positions and the momentum. The initial states are initialized with Gaussian distributions. The configuration parameters are 6. They're constant global parameters, and here I'm reporting what they correspond to. An important consideration is that while these are 6 fixed parameters that are associated with components of settings of the actual accelerator, their influence on each particle is different. Because, I mean, this is in an intuitive way, if we set a magnet in a certain way, the effect of that magnet on particles that are located in different places is different. And this is just an example of, based on the position of the variable, of the particle, which is on the horizontal axis, we see how the effect of a certain component is different for each particle. And so while for now we're just considering fixed parameters, constant all over the domain, the next step is to do a position-dependent setting. Now, what are the architectures that we consider? Pushed by the nature of the data set, which is a point cloud, we considered point nets, which proved to be effective for this type of data. But clearly, modifications to the original architectures are needed for our specific physical setting. So we have 2 inputs, as I mentioned, the states, so positions and momenta, and the settings. We have an input transform that can be seen as a projection into a canonical space that guarantees translation and rotation invariance. It's like, think about projecting your system into principal coordinates, for example. Then for the transformed input, node-wise, or point-wise, we apply an encoder and obtain encoded point features. We concatenate to these the settings and do the same operations, but we save the point features and we attach a max pooling, so a global feature to them. And this step, the attaching the global feature, is how we take
Your voice is breaking, Marta, again.
the
We can't hear you.
interactions within the points. We have coded project. I'm so sorry. Is it any better now?
Yes, I can. So can you just repeat what you said, your last statement? We still cannot hear you. It's breaking down.
We
Okay, let's wait Siddharth for a couple of...
Yes, yes, I think she's reconnecting. Okay.
Okay.
Let's try again, and I apologize. Can you hear me?
Yes, we can hear you.
I am really sorry about this.
No worry, no worry.
Okay. So I went over the point net, and I'm now switching to the graph net, although I already described it a little bit before. the GraphNet is exactly a message passing graph neural network where the settings are passed as global variables, and for now they're concatenated to the attributes. We have more than 4,000 beam accelerator simulations, and the way we initialize the GraphNet is by clearly putting on the points, on the nodes, the state variables, and on the edges, which is very common, for example, for Mesh GraphNet, the signed distance and the Euclidean distance between points. So our first study was really just a comparison of, let me say, popular architectures and baseline architectures that were used for this problem in the past. So what we have here, we're in phase space. So we have X and the momentum in X, Y and momentum in Y, and so on. The metric for the accuracy that is relevant for this simulation is the emittance in X, which is a function of the coordinate and the corresponding momentum. And these are relative errors for that quantity.
Marta,
So
just one question.
Yeah.
So for this problem, are you just incorporating the data or any kind of physics also?
Only the translation and rotation invariance and the permutation symmetry. But the permutation symmetry simply says that the edges are the same. So the message between I and J is the same as the message between J and I.
Okay. So, and that you can incorporate using the inductive bias, right? Directly into the modifying the architecture.
Yeah, exactly.
Okay. Thank you.
So yes, and so this is done for the GraphNet. We use the graph transformer as is, meaning we do not touch the architecture. Clearly, we tune its parameters. This is the point net that I introduced before, and this is the graph convolutional network that was used in the past, and for this reason is used for us as a baseline. What we can see from here is that the graph network performs best. Now, there's a lot to say about the bad performance of the point net, and I think it's due to the fact that we're not exploiting that architecture in the right way, meaning that and we're working on it right now. And I'm going to give these considerations now because I'm not going to show any results for point net anymore. So we have this initial input transformation that can be seen as a projection into canonical space. And we are applying it to the whole state vector, meaning to x, y, z, and px, py, pz. While this transformation the canonical transformation should be only applied to the coordinates. So I think there is a chance for point nets to provide better results, and we're working on it, because this result is in a way not really expected. Here we have a visual comparison just to see how strikingly better the message passing graph neural net is compared to the baseline. And by the way, I'm writing Mesh GraphNet, but it's a modified Mesh GraphNet with the invariances that I talked about. And also it's Mesh GraphNets were introduced for time-dependent problems. Here we're just doing a one-shot type of approach from initial configuration to final configuration. Here we're comparing the GraphNet with a baseline with some quantitative results. So here we're in phase space for X, Y, and Z, and there's the emittance error in X, Y, and Z, and it's a relative error. So and this is the highest error in the validation data set. So this is considered excellent as the highest error. And this is an absolute error over the whole variables. And this is the lowest error. So clearly the GraphNet truly outperforming the previous architectures that were used for the specific problem. Now, what are we working on? We're working on the autoregressive architecture to track time evolution. And in this specific case, we need several modifications to the network to incorporate changing settings as the position changes. As I mentioned before, we would like to impose the machine settings pointwise, and pointwise means that the settings affect particles in different ways depending on their positions. And as the particles move, the settings affect the moving particles in different ways. So this is a non-trivial modification of the architecture. Another thing is, as I mentioned before, is a better implementation of the point net to make sure we are correctly projecting the states into canonical space. I wanted to mention additional works on graph networks at Stanford, and I'm happy to talk more about them separately and offline. We're working on better pooling approaches, as I mentioned at the beginning, that take into account information in latent space, so select nodes in latent space that carry more information, but that at the same time keep the graph well connected. And we're also considering graph nets in the context of DDAC, so discrete exterior calculus, applied to subsurface transport. I think a big question, though, that is very, very important in industry is how do we know what architecture we should use given a data set and some metadata regarding the problem? Because, I at the beginning, I talked about what to do in the context of mechanics, what to do, or what the challenges are in the context of CFD. But given a data set, how do we know without, an engineer in the loop, what architecture we should set up? And I think this is where generative AI can really make the difference. And so this connects what I wanted to say about an opportunity that we currently have for PhD students in our company, and it's the use of generative AI in the context of both neural operators, physics-informed machine learning, and design, and in particular applied to design. So if you're a third-year PhD student and you're interested in these topics and have some experience, do reach out with your CV, and I'm happy to get back to you. And with this, I conclude. Better to conclude given my unstable connection, and I really, really apologize for the technical difficulties.
Thanks, Marta. Siddharth?
Thanks, Martha, for this amazing talk. And before I get into my question, I'd like to just check with the participants if you have any questions in specific. And if not, I'd like to just have a quick question on the architecture that you showed for the point networks.
Yeah.
So when you really look into the input points and the settings, it typically in the particle accelerator simulation problem that you just showed a few moments ago, I'm wondering settings, I believe it's going to be larger in size compared to the input points. Am I right to say that, or is it not the case?
No, it could be, right.
Right. Okay.
It's a choice that you make. I don't think it's ever above 1,000, honestly. I really doubt that, because here we have 2,000 particles, but the settings that we consider, well, first there are 6, so they're not a lot.
Okay.
And they were selected by our collaborators at SLAC as the settings that are most influential on the particles. Clearly, the accelerator is not defined only by these 6. settings, but they were considered the most important for this application.
Sure. Thank you for that. And so you talked also about an encoder, or maybe called more like an input transform that you were doing. So is it like, so are you typically just dealing with the input, the coordinates and the momentum? Is that what you mean as the input point?
Correct. Yeah, correct.
And then you would be transforming that into like a reduced space, if I'm right in that sense.
So not in this case, or let me rephrase that. What we are trying to do here is basically to project our variables into a canonical space so that, let's say at some point you get the same point cloud, same position, same momenta, but rotated or translated.
Right.
The network doesn't see this. The network thinks that they are exactly the same, as it should. The encoding happens here, and it's exactly the same encoder for every, let me call it, projected state. This is very similar to graph nets, where every node and every edge is encoded in exactly the same way. And it makes it, by doing this, the network generalizes to different points, different number of points, different number of particles.
Okay, I think that makes it clear for me, right? Because like I think you're trying to like include the features of a typical graph network into explicitly into your point networks. Am I right? I think that is what you're doing, right? I mean, when you
yeah, and I honestly think that the challenge here is to include interactions between particles. And so one thing that is missing, I think we need to work better on the input transfer. And the other thing is the interactions between points is only taken into account in this max pooling operation. And I don't think this is enough. So maybe even a super shallow graph net would work. Like we need some better mixing when we consider interactions between particles. A good way to mix would be clearly just to put a feed-forward neural network, that considers all these points at the same time. But this doesn't generalize, meaning if I put an MLP for that is not shared, and then I have a different number of particles, I mean, the MLP is constrained to work only for the number of particles it was trained for. And that's why I'm thinking that maybe putting a graph net at this point, just for mixing, could help.
Sure. Okay. And also, like, when you talk about max pooling, like from convolutional networks, I think what we understand is like it basically averages out some features from your structured domain. So when you think about point clouds, as you're dealing with in this case, it is reasonable to say that you're averaging out a set of points in the domain, and you're basically
and that's why I think it's not enough.
Okay. Thank you for that. I think that makes sense. Thank you for that, clarifying my question.
Sure.
So
just one comment, Marta. Since you mentioned you're working on the subsurface transport with one of your PhD, so are you using graph networks there?
No, I mean, we want to compare them with regular graph networks, but we're basically working with graph data using discrete exterior calculus type of approach, where we basically learn the diffusion matrices in the system. So it's a typical diffusion problem where we're learning generalizable diffusion matrices for graph type data.
Okay.
I'm happy to share a reference.
Yeah, no, why I'm asking, because recently we just put a paper on Archive where we are actually solving a fractured porous media.
Oh, wonderful.
Using pins, and basically we use a real 3D data for that.
Yeah. Please share with me. I'm sure I missed it.
Sure. And coincidentally, we got that data from Stanford only. Professor Anthony Kosek. He's, I think, Department of Energy Science and Engineering, Stanford.
I'm often there because Daniel Tartakovsky is in that department. and Daniel is the person I'm working with for this specific problem. So yeah, please share. It would be great if you could share your paper with me.
Sure. Definitely. I'll send you the paper. By
Thank
the way,
you.
on a lighter note, are you just looking for a PhD student, or you're also interested in a master who want to do some internships?
So we're looking for, and I can tell you why. We ask for at least 2 years of PhD. And the
Uh-huh.
reason is simply that we would like some research experience, like
Okay.
and especially in some sort of generative AI. I know that generative AI for physics is not super popular yet, and it's hard to find people with experience there. But if we find a person that at least has some knowledge in that direction and has done some research work in their academic career, that would be very much preferred.
Okay. I just casually ask. Yeah.
No, thanks for asking. It's a good question.
Thanks, Marta, for a great talk, and it was
No,
really
thank you for having me. I really apologize about the technical difficulties.
no worries. So it was great. So I'll just stop the recording here.